Okay, what is Lagrange interpolation? Well, if you have x0, y0, x1, y1, and all the way up to, let's just do, was there 0 before? Not 0 in there, was there? The smallest one was 1. Let's just do 1 then. 1, 1. This 2, 2. All the way up to n, y, n. Okay. So basically, if you have n points on a graph, or like a plane, n points on a plane, there's exactly one polynomial of degree n minus 2 that passes through all those points, as long as, the points are like the x's are all distinct. It's like a function, Obviously, so the reason is basically because the coefficients of a polynomial determine the polynomial, and if there's degree n minus 1, there's a plus the constant term, there's n coefficients to determine. Okay. So what Lagrange interpolation does is not only does it tell you that the polynomial is determined, which is, I guess, obvious, it tells you a formula for it. So the formula is something like this. Sum of YLs, okay, and then it's the product of x minus x I, say, on xl minus xi, and this is I not equal to L. Um, and this is the sum of L equals 1 to n. Yeah, so this is a polynomial in x, okay, so notice this is a variable. So this is the variable x, yeah? And all the other things are actually just numbers. But notice when you sub in x equals xl, right? What happens? Well, see, the top becomes xl, the top becomes the same as the bottom, right? So this term just becomes 1. Yeah, so this term just becomes 1 when I is never equal to L, right? Um, but when I could be L, that's when you'll get 0, right? So all the other terms you'll get 0, and you'll get YL. So it has to be the right polynomial, right? So I remember we were doing some, like, there's a straight line that goes through 2 points, right? There's a formula for the straight line. So this is like the polynomial version of that, okay? Lagrange interpolation. Have we seen this before? I'm sure we have. So do people remember it? Hurts brain. Ooh, there shouldn't usually be pain associated with this. Um, hmm. Okay, so let's see how Lagrange interpolation is used. So our thing is kind of like, since both sides of the identity are rational functions, it suffices to prove it when all the x are not plus or minus 1. Hmm. Okay, so try to remember this formula here. This is the polynomial, Lagrange interpolation. So now we're back to this problem. Okay. It suffices to show the result when they're all not plus or minus 1. Hmm. Yeah. About that. So I guess what we're saying is um, something that's true for all, but a finite number of x's will still allow you to conclude the thing is true as rational functions. But the thing is, when x is plus or minus 1, it's very simple to deal with. So I don't think that's a big deal. So we can assume xi is not plus or minus 1. I mean, if xi is plus or minus 1 in this, let me just go back. So we have basically a sum of I equals 1 to n, a product of j is not equal to I, 1 minus xj. So we're trying to show that that is equal to 1 or 0. So what if xi, so if xi is equal to 1, okay. So can you see what happens? Basically, it just remove it takes basically it takes it takes out a 1 and subtracts something which looks like the lowered like one less variable case. Something like that, okay, with one less variable. So I don't think it's a worry if it's 1, because you're still trying to solve a problem like this in the end anyway. And if they're all 1, then you just keep reducing it. So even though they're not really allowed to be the same, I guess, but only one of them could be 1. Okay, what if it was -1? If it was -1, it'd be like 1 plus xj on -1 minus xj. Ooh. So all of those have become -1s. Oh. So if xi equals -1, then the term that with the I equals, it's the product, the summand with I, with that I, would turn into a -1 to the power of, so there's as many -1s as there are variables not equal to I, so that's n-1, you know? And what's left in the other parts The other parts will have, there'll be one thing in every other part with a j that's not equal to that. So for every other thing, the xj equals -1 will give you a 1 minus xi on xi, but 1 plus xi on xi plus 1. So that should just all cancel out to be 1. Okay, so what that tells you what happens is it's 1 plus what happens in the lower case, the lower variable case. So if n is odd, then it'll be 1 plus what happens when n is even. When n is even, it's 0. Okay. Okay, so when n is even, it'll give you -1 plus what happens when n is odd, which is 1. So it'll be 0. Yeah, so definitely 1 and -1 are really not worth considering. So define a polynomial f of t equals the product from I equals 1 to n 1 minus xi of t. Yeah, okay, so consider this polynomial in t. Note that if you sub in one of the variables, you get f of xi equals, what do you get? Well, you get 1 minus xi squared product of j is not equal to I 1 minus xi j. Okay, so that's kind of like the numerator of some of these terms. Okay. Okay, using node +1 -1 x1 up to xn. Okay, so now we're starting to get using +or -1 x1 x2 to xn. The Lagrange interpolation formula gives us the following expression for f. Okay, let's do this. So I'm not quite sure where the screen goes up to now. Let's try it. So we get sum I equals 1. Actually, we could probably do this without looking at the formula because we know what Lagrange interpretation is, right? Because we know that it has to output. So the y's are f of xi's. Um, um, so I guess there's also an f of 1 and f of minus 1 involved. Uh, so for all the f of xi's, you have to times it by the product of all those things, remember? So it's like x minus 1 times x plus 1 on x I minus 1 I plus 1. So this is using exactly the formula for Lagrange interpolation that we just showed, right? Interpol. There's going to be x, it's minus everything, every one of those other variables. So it keeps going to become j is not equal to I. So I don't need to look at this to write this down because I know what the formula is and I'm applying it to these numbers, yeah? So j is not equal to I, x minus xj on xi minus xj. And then there should be another term for f of 1. Yeah. F of 1. Where you have like all the stuff that's not equal to 1, right? So like x plus 1, x, no, this will be now 1 minus x. It's a 1, 1 plus 1, I guess. You don't have x minus 1 anymore because that's 1. You still have this product of j is not equal to 1. Oh, no, you just have a product of all j. Because it's not excluding anything anymore. So then it's x minus xj on 1 minus xj. And of course, there's one more term with the f of minus 1. Yeah. Plus. Wonder if it'll show. One and negative 1 gives 0. Okay, so this is f of minus 1, and it's going to be x minus 1 on minus 1 minus 1 product of all the j's. X minus j on minus 1 minus xj. How much of that made it? Oh, it looks like it all made it. Okay, good. So let's be clear about what's just happened, okay? So it's the Lagrange interpolation for a polynomial in T, okay? So that's f of T. It's this thing at the top here, okay? Okay, so no, okay, I guess we're writing t as x now, but um okay, so one observation is that um the coefficient of t to the n plus 1, okay, is 0 because it has degree n, right? It doesn't get up to n plus 1, okay? But um oh, that's weird. So it's doing interpolation. So it has degree n, and we need n plus 1 points, but we actually use n plus 2 points. So I guess it's kind of nice that it's not contradicting. Hmm, interesting, huh? It's not contradicting because it can't contradict. So, but what is, okay, but what is the coefficient of t to the n plus 1 here? Oh, interesting. Or in other words, coefficient of x to the n plus 1. Think of these as t's, or you can think of them as x's, it doesn't really matter, but they're the variable in the polynomial. And as written here, so because we use the Lagrange interpolation for n plus 2 points, we're going to get an extra degree that needs to be 0. So what is that extra degree? What are all the degree n plus 1 terms? Well, the coefficients should add up to, so it should just be f of xi over, it's not going to fit, is it? I'm going to erase. It's just f of xi over all this other stuff, like xi minus 1, xi plus 1, product of 1 over xi minus xj, sum over I, plus, what is it? Oh, wait a minute. J not equals to I, so there's n minus 1 there, then plus 1, yeah? What about all the other ones? All the other ones, there's also n plus 1, because there's n in the product and there's 1 outside. So it's plus f of 1 on 2 times product of j 1 on 1 minus xj. Okay. Plus f of -1 -2 product 1 on -1 minus xj. Does it agree? Yeah, it agrees. Uh-huh. Uh-huh. Oh, Kai Bing said something earlier that's relevant now, I think. Oh, so what is f of 1? F of 1 is just 1 minus xi. So f of 1 is just 1 minus, yeah, so if you look at it, yeah, so if you look at this thing here in red, this is actually pretty much the original question because um um f of x I x j. Oh, that's why they introduced the x1. It's because of this 1 minus x squared cancels. Okay. Yeah. So basically what this thing equals is it equals the original question. So this is the expression. So this is the expression in the original question. Okay. Noting that when this is equal to xi, this part cancels with this part. So okay, and I think the f of 1 is just the 1 minus xj, so this cancels with that, yeah? And f of -1 is 1 plus xi, so it cancels with the bottom up to the sign, yeah? So you get a -1 to the power of n. Okay. Ah, wow. That solves the problem. Because that's the thing you want to have originally, and that's the coefficient of t to the n plus 1 has to be 0, right? So the thing that you wanted to show, so this is like the question. The question plus, oops, the question plus half plus -1 to the n on -2 equals 0. Yeah. So the question is equal to minus, so it's minus, yeah, so then when n is even, right? When n is even, it's equal to 0. This is equal to 0. So q is equal to 0. When n is even. If n is odd, what do you get? You get You get a half plus a half. So Q is -1. Um, okay. So it's Q is 1. This is minus Q actually, because this is the negative of 1. So 1 minus x squared is the negative of this. Okay. So that's a pretty cool answer too, by Lagrange interpolation. Ah, that was pretty cool. Lagrange interpolation. So that's an interesting way to use it, huh? So even if you have even if you have a lot more points than you need, um, I guess as long as you knew that the polynomial was gonna fit, then the formula's still true for that polynomial. Hmm. Yeah, and this question, I guess, is very well suited because the question in the formula is very similar to the Lagrange interpolation formula. Lagrange interpolation. Yeah, so it's not just that it's determined, but it actually tells you the formula for it. Okay, that's pretty cool.